Yeah, thank you. So this is joint work with a whole list of people. And if you look at the affiliations, there are from 4 major companies, all of which are building web browsers. And I'm going to talk about WebAssembly. So what is that? So in a nutshell, WebAssembly is closer to the microphone. Okay, so I can hardly move. Okay. So WebAssembly is a new code format, a portable code format, the purpose of which is to bring native code performance or near native code performance to the web, so to the browsers that you run on your machine. And of course, the motivation for that is to allow you to run like high performance applications that are computational intensive, like 3D or audio video stuff or games, things like that in your browser. And one thing that's remarkable about it is that I think it's one of the first times that a major web technology was actually developed not by one company, but by 4 companies in collaboration. So we all designed it together. We all implemented simultaneously, and it's all already shipping in 2 of these 4 browsers and will ship soon in the other 2. So it's already in the experimental builds. But despite this being an industrial project, it's a completely open standard. So it's done under the roof of the W3C. All the discussions are in the public on GitHub, so you can actually follow everything if you're interested and have your voice heard even. And it's not proprietary, copyrighted, or painted in any way other than other well-known technologies in that space. So why did we do that? Well, I already mentioned computationally intensive things on the web, so that means we want to provide high performance on the web. And by that we mean close to native code performance. But not only like high peak performance, actually what's probably even more important is predictable performance, because the other execution format on the web with this JavaScript is actually pretty good these days in terms of peak performance, but the problem with it, it's highly unpredictable. And you have performance cliffs all over the place. So you just like increasing your data set by one element might give you a 100x slowdown in some weird cases. So that is not supposed to happen with WebAssembly. And then the other thing is that we want to kind of liberate the web from the stranglehold of JavaScript. So empower it to run other languages than JavaScript without having to jump through hoops by compiling it to JavaScript. And that also implies that we want to enable features that JavaScript doesn't provide. So if your programming language has features that you cannot compile to JavaScript right now, then you're basically doomed. So with WebAssembly, we want to change that. And you may be aware that there have been other technologies in the similar space, notably ASM.js and Knuckle or Pinnacle in the recent years. And you may be thrilled to hear that both the teams that did these technologies are now part of the WebAssembly team. So we all converge on WebAssembly now. They're all working on that. And these 2 technologies are more or less deprecated at this point. So WebAssembly will replace them in all the browsers. So when you build a technology like that, obviously you have a couple of goals, and I just want to briefly list like a few of them, or actually it's quite a number. So first of all, we're building a kind of language here, and it's supposed to be portable. So that has several dimensions listed there, and it's supposed to be fast, of course, and we're running in the web, so it also has to be safe and things like that. So all of that is about the semantics of this language. But on the web, since you transfer code over the wire, there's another dimension, which is the size of the code in particular, so the representation. So we want this code to be compact, and we want it to be easy to process. In particular, it should be easy to compile on your web browser to native code. So all these things were part of the design we were looking for. And it's even designed so that you can parallelize compilation, you can stream it, so you can start it when you haven't even seen the full binary and things like that. So I'm going to run you through some of the basic points of the design. The first one is probably not surprising, it's a bytecode, right? Because it has to be portable. So that's about the only choice. And this bytecode is specifically designed to support JITting well. So it's not designed for interpretation that much than for JITting to native code. The next thing is the computational model of WebAssembly is that of a stack machine. And while that is maybe a bit more unusual with respect to real assembly languages, it's not unusual at all when you look at other VMs or things like the JVM. And the main reason we did that, so many people ask why don't you use like some 3 address code or some other IR, is that this is the most compact way to represent a lot of code, especially when you have a compilation of expressions. The stack machine is the most compact way to represent that. But I should mention that the stack here is not like a dynamic thing, really. It's entirely static in the sense that at every point in the program, you know what the stack is, what the layout of the stack is. So one way to think about it is really it's just a set of virtual registers that are addressed implicitly and relatively by the opcodes. So there's nothing really dynamic about it in that sense. And then we call it assembly language basically because it represents what the hardware gives you. So all the types it really has are just the types that your CPU gives you. So numbers, that's all there is. And similarly, the operators, the basic operators it provides are the operators you get on the hardware. So those were kind of like maybe less surprising things. There are also a couple of design choices that may be a bit more surprising. So the first is what we call linear memory. So in WebAssembly, we don't have any kind of object model or something like that built in. Everything you get is just a huge array of raw bytes. That's what you operate on as your memory. And you can access that like you would access the memory of a real hardware with all sorts of operations that allow you to write stuff into it and read it out. And so you basically use integers as pointers. That's how you can compile low-level languages to it. In addition, this memory to be safe, of course, has to be bounce checked. So that's one difference to actual hardware, although you could argue that memory MMUs are also kind of implementing that. And we're actually implementing that where possible with hardware support. And finally, this memory is also growable. So that gives you the ability to simulate something like getting more memory from the OS for your process. The other thing, which is probably most surprising and also probably the most controversial design choice in WebAssembly, is that we don't have arbitrary jumps. We only have structured control flow. So there are blocks and breaks which allow you to break out of a block or a nested block, but you cannot arbitrarily jump around. So that means that we don't have irreducible control flow by construction. And that has a bunch of benefits. In particular, it makes it much easier and faster to validate the bytecode and to compile it, and you avoid a whole bunch of issues. And it turns out that, most languages don't actually allow irreducible control flow. And even the ones that do, most programs don't use it. So in the few cases where you have to use it, you have to resort to an algorithm that was invented in the context of ASM.js by Alon Zakai, the relooper algorithm that allows you to transform irreducible control flow into reducible control flow. And in practice, that actually works sufficiently well for the cases where you need it. And finally, again, due to safety, this language is typed. The type system is primitive, but there are types, and the type system ensures that the language is type safe and memory safe. So, and it also ensures, I already mentioned that the stack layout is static, and that is ensured by the type system. The type system tells you what the stack is. So it's also important for mapping this efficiently to hardware registers and stuff like that. And this is not just a type system we just invented on paper and wrote some nice sentences about it. We actually formalized it, and it's sound. I'm going to get back to that. And finally, the way WebAssembly programs are structured is they are organized into modules. So a WebAssembly binary is a module, and a module can import and export stuff, but it can't do anything else. So it doesn't have any access to the ambient environment at all. Everything it wants to do, it has to import. And on the web in particular, what it can import is what we call host functions. So in that case, JavaScript functions. And that is a way to provide you access to all the web APIs. There's no other way to give you that access. So in a sense, we use JavaScript as our FFI on the web. Okay, so that was like the basic design. I want to briefly flash at you the language. So I said it's a binary format, but you can think of it as a language, and this would be the abstract syntax of that language. So I won't go through that, but you see here there are like a bunch of types on the top and various instructions, and on the bottom you see that a module is basically just a sequence of definitions of various things. And the binary format is basically just a serialization of this AST that we built with that. So here's an example. So it's a binary format, but we also have a text representation. And that happens to be an S expression form, which is something we just did because we didn't want to bike shed syntax early on, and then something happened that never happened in history before. We got stuck with it. So this is just a simple example of a module with a simple recursive factorial function. So in pseudocode, it would look something like this. And in bytecode, it would look something like this, just to give you an idea what this code looks like. What's interesting about WebAssembly and what is actually the main focus of this paper is that we have a formal specification. So we have a complete formal semantics of the entire language, and we designed that in lockstep with the actual design itself. And at first iteration, in the disguise of a reference interpreter written in OCaml, but it was written in a style that is basically a transliteration of the formal rules into OCaml. So formal semantics consists of two parts, if you know about these things. So one is the operational semantics, so how it's actually executed. And we really formalize that in completely standard small step reduction relation, which is maybe somewhat unusual for a stack machine, but actually works out quite well. And this semantics is almost entirely deterministic, so it's all well defined with a single caveat, and that is the exact bit patterns for nans, which we just couldn't lock down because CPU and hardware just differ too widely to make that feasible. It would be a high performance cost if we did so. So we had to bite and to make that little compromise there. So there's no undefined behavior here and no implementation defined behavior. And just to give you an idea, just want to flash that briefly too. This is one page of our paper. Don't worry if you can't read it, just to give you an idea. This is the entire operational semantics of the language on one page. Modulo what all the numeric primitives exactly do, but all the execution semantics is there. And the other part of a formalization is the static semantics, so the type system. And again, we just used like completely standard methods, like typing rules, and the type system overall is almost embarrassingly simple, which of course is by design because it's supposed to be easy to validate and fast and so on. And yeah, I already mentioned that this ensures that the stack layout is known. It also ensures various other properties like encapsulation and some compositionality properties, which I don't really have time to go into. But on top of that, we also have not just given this type system, we have even proved its sound. There's a paper proof in the paper has the theorem there. There's a paper proof, but after we submitted the paper, Konrad Watt, who is now a PhD with Peter Sewell in Cambridge and used to be an intern of mine at Google, took our paper, put it all in Isabelle, and proved its sound. So we now not only have a soundness proof, we actually have a machine-verified soundness proof of WebAssembly. And as far as I know, this is the first language coming out of industry that provides that, from the get-go. So I think that's pretty cool. And again, the type system is super simple. If you can read typing rules, there's nothing fancy going on here at all. So this is not even a full page. And you might be more impressed by this if you if you realize that the same thing for the JVM, for example, the bytecode verification in the JVM, which would correspond to that roughly, takes 150 pages to specify. So by doing this with the formalization, you actually have a feedback loop that gives you a much cleaner and nicer design in the end. And we didn't just want to have a paper specification, but we actually want to put that in the official language specification. So I'm currently writing that, mostly through with that, and it includes everything that's in the paper. I don't know if that link is going to work, just to give you an idea. Yeah, so here's the web page, and if I click on validation, for example, let's say, I don't know, control instructions. So yeah, so this, for example, is the official specification of validation for control instructions, and you can just see the normal typing rules there, and then you have some prose that's basically the same rendered into text for those people who are too scared to read the formal notation. Right, so that's that. I want to briefly talk about implementations too, because this is PLDI as well. So I already mentioned this is implemented in all the 4 major browsers. And one thing that's interesting about it is we all implement it in somewhat different ways. So the point of the slide is in a way to demonstrate that the design is actually pretty flexible, but also that we're still in early days, so we haven't really found the ideal way necessarily to implement it. We are still experimenting with different approaches, and I expect us to converge over time more than we do now, but all of these approaches work, at least. They have different trade-offs in terms of startup times and jank and stuff like that. And of course, we also apply all sorts of tricks in the implementation, optimizations, the ones that you might expect, plus some more. I don't have time to go through that, but if you're interested, there's quite some discussion of that in the paper too. I want to skip forward to performance numbers because, well, we make the claim this is fast and compact, so we measured that. So this is measured on the Polybench C benchmark. And the 100% line is its execution time of the individual benchmarks in the suite on as native code on x86 64-bit, just compiled with Clang, I think. And the bars are, the blue parts of the bar are basically the execution on the same architecture in WebAssembly. And as you can see, for most of these benchmarks, we are already like close to the goal, sometimes even beyond that. You can see quite a bit more in that graph, which is like compilation time. So the orange stuff is the actual compilation time, the JIT time that it takes. And it's relatively good already, although we are still working to improve it. What you can also see, or rather not see, is the validation time. So how long it does take to type check the modules. And these don't actually show up in the graphs because they're so small that you can't see them. So validation is really super fast, which was also the design goal. We can validate the code as the speed of the wire, basically, at the speed of the wire. So the other important dimension was code size. And here's like a scatter graph that tries to measure that against, again, x86 native code, but also ASM.js code. So if you look at the blue dots painted against native code. So every dot is the size in WebAssembly against the size in native code, and the diagonal is basically where they are the same size. So everything below the diagonal means that WebAssembly code is smaller. And as you can see, it's actually pretty good. And the orange dots are the same kind of measurement against ASM.js. So we're also smaller than that. And yeah, so this is kind of what is shipping now. What I'm describing and what's described in the paper is version 1.0 of WebAssembly. And that was specifically targeted to allow you to compile C code to the web. But there's a bunch more things we want to do in the future. So one is, first of all, we don't actually view it as merely a web technology. We have been very careful to layer the design such that you can have standalone implementations of WebAssembly, basically as a VM or a virtual ISA. So we really would want to see standalone, or want to build standalone implementations in the future, so that you can all map your languages to that and have a nice platform to work with. And the other thing is to extend, of course, the support of language features, and that particularly means better support for more high-level languages. So here are like a bunch of features that you might want to see, which are not in there yet. Two of them are actually have already been implemented, Threads and SIMD, and at least Threads are probably going to get into the language this year. SIMD maybe sometime early next year. And then there are other things which are also, I would hope, not in the far future. So we're already thinking about these garbage collection in particular is probably the most interesting feature in terms of higher level languages. And we're already thinking about designs for that too. Oh, exceptions is actually also already prototyped. So that's where we want to go in the future. And yeah, this is my last slide. So to sum up, it's a new code format. It's portable, it's compact and efficient. And it already runs everywhere. But we don't just view it as something for the web or actually assembly language. So in a way, the name is actually misleading. And I also want to stress the point that designing a language along with the formal semantics is actually not just possible these days, even for an industrial language. It's actually beneficial. It ultimately leads to a cleaner and simpler design, as we saw here. So I encourage everybody in this community to actually push that forward and get us out of the state of the art of the 1960s with respect to the way how we define languages. And yeah, there's a web page with demos and everything, so I didn't have a flashy demo here, but there's a demo there that uses the Unity engine, I think. There's also one that uses the Unreal engine, although I'm not sure that's public, actually. But yeah, you can look there. And that's all I wanted to present.
Can you elaborate on the decision of linear memory and how that's working out for you?
How's that? What? Sorry?
How is it working out for you?
How's that working out for us? For us, it's simple. You have to ask the compiler guys that target. No, but no. So that is what you want when you compile a language like C, right? You have one linear address space. That's what you can map everything into. So as I said, your pointers are just integers, and you don't have to do any complicated transformation on the way you deal with addresses and pointers. So in that space, it's and it's proven technology from ASM.js as well. So this design is essentially following ASM.js precedents, and so you can almost plug in and replace it with that. So in that sense, it's working sufficiently well.
Hi. How do you balance the trade-offs in keeping assembly low level and then also trying to support higher level features like exceptions?
That's a very good question. That's always like a tension there, right? I mean, so far with the version 1.0, we don't have any like high level feature. But things like exceptions or also GC kind of force you to go a bit more high level because we're in this unique space. Like unlike real assembly language, we have to stay safe, right? That's a absolutely hard constraint that it has to be safe and portable. And that makes certain things harder, so you sometimes need to go to a higher abstraction level to maintain those. And yeah, I mean, for every such feature, you have to find the right sweet spot. As low level as possible, but no lower.
Oh, great stuff, super exciting. I'm curious about the thoughts of you and your authors and the implementers on the FFI. Right, you got to talk to JavaScript, or if you move it to another domain, and in specifically about whether the JavaScript is allowed to peek and poke the memory, which seems like a tough trade-off between paying performance for marshalling and unmarshalling, or giving up compiler optimization because any FFI call can havoc your memory.
So the linear memory is just something that a module can declare, and it can also declare to export or import it. And on the JavaScript side, it just materializes as an array buffer. So you can just use the usual typed array interfaces to access it in the ordinary way. And when we add threads soon, then it will actually be a shared array buffer. So I don't know if you're aware of that. They were actually added to JavaScript to support WebAssembly threads. So yes, you can peek and poke from the JavaScript side, and then you just see a typed array. If you export it, otherwise it's encapsulated. Okay, thank you. Thank you.